Hello there and welcome to another video lesson. Today I'm going to be discussing closed systems, and it's going to be operating under ideal conditions. So we've got a container, as you can see on the screen. It's got a closed container with air in it and then a little bit of water at the bottom. It's given by initial pressure 101,325 pascals, initial temperature 298 Kelvin, so just ideal conditions. It's got a total volume of 0.01 meters cubed, and the mass of the water is 1 kilogram. And so our goal is to find out the temperature when we have a final pressure of 200,000 pascals. And so we're going to go about doing this. First, we notice that we have two different substances in the container, air and water, and we need to find the pressures of both of them. So we're going to go ahead and find out the partial pressures of the air and the partial pressure of the water. And so in my last video, I talked about the Antone equation, and we did a whole lecture on how you can do linear regression and nonlinear regression with the Antone equation. We did that in Python, and today I'm also going to be using Python again. And because I've already done the Antone equation, I found a tool in Python that actually uses a more powerful version of the Antone equation, and it lets us find the vapor pressure of water much faster. So I'm going to go ahead and use that. So we know the partial pressure of the water, and so we need to find the partial pressure of the air. And because we're at ideal conditions, we can go ahead and do that. So we know that pressure is equal to moles times R, and then R is just the gas constant, equal to 8.314 joules per mole Kelvin. Alright, so we're going to want to know the number of moles of air, because we're dealing with the partial pressure of air. So that's going to be multiplied by the gas constant times the temperature over the volume, and the volume of what? The volume of the vapor pressure. Alright, so we don't know the vapor pressure right off the bat, but we do know the total volume. So what we can do is set the volume of the vapor pressure equal to the volume total, and then we want that to be plus the volume of water. And we know that the volume of water, oh, that should be a minus sign. We know that the volume of water, we can find that by knowing that the mass over the density is equal to the volume. So we know the mass of water, because that's one of our initial conditions, and then we can just divide by the density of the water. And so now we know the volume of the water, and now we know all the parts that are super relevant in this equation. So we can go ahead and apply our partial pressure equations and plug in our initial conditions. So we know the initial pressure is equal to the moles of air times the gas constant times the initial temperature over the volume of the vapor pressure, and then plus the partial pressure of the water. And so we notice that we don't actually have a value, or we don't know what the number of moles of air is. So we're just going to go ahead and solve for that. And I'll explain why in a second. So we're just going to go ahead and manipulate this. Keep it pretty looking. So we know that the initial pressure minus the pressure of the water times the volume of the vapor pressure over the gas constant times the initial temperature. And so now that we solved for the number of moles of air, and because it's a closed system, nothing's going in, nothing's going out, we can go ahead and do the same process but with our final pressure. So we can do the pressure is equal to the number of moles of air times our gas constant times the final temperature over the volume of the vapor pressure, and plus here. And so now we know everything in this equation except for the final temperature. And because we're going to be using a root solver in Python, we're going to go ahead and set this equal to 0 and then just subtract over the final pressure. So we end up with an expression that looks like this. Alright, so that gets us these conditions here. But I want to discuss some further conditions. So I want to discuss what would we have to do if we no longer knew our volume total. So we no longer know the volume total. Instead, what would happen if we knew a number of moles for water vapor? So say we had a number of moles of water vapor, and say that we've got 0.3 moles of water vapor. And so that kind of throws a wrench in our expression here. So we can find out the volume of water in our container, because we still have this initial mass of the water, but we want to find out the mass of the water vapor in the container. And we have moles, which makes it really easy for us to find the weight, or not the weight, the mass of the water vapor, just by multiplying by the molar mass. So we're going to go ahead and multiply this by the molar mass, and then that'll give us grams. We want kilograms. That was what our initial condition was, so we're going to go ahead and divide by 1,000, and this is going to be equal to the mass of the water vapor. And now that we have that, we can go ahead and solve for the volume of water in the container. And so we want the mass of the water, liquid water, minus the mass of the water vapor. And because we want volume, we're going to go ahead and divide by the density of the water. Alright, so now that we know that, we want to go ahead and input these new values we found into the ideal gas law. So we've got the pressure of water times the volume of the vapor pressure. We're going to set that equal to the number of moles of the water vapor. And we want to go ahead and multiply by the gas constant again, and since we want the final temperature, we're going to go ahead and use the final temperature. And so now we have a desired number of moles that we want. We want to solve for the actual number of moles that we're going to have. So we're just going to go ahead and do one final manipulation. And we see that we've got the number of moles of water vapor is equal to the water pressure, or pressure of the water, times the volume of the vapor, and divided by that, the gas constant times the final temperature. And so now that we have all that, I'm going to go ahead and move over to the Python code, because we have everything we need to go ahead and code out these two initial conditions. Alright, so now I have our Jupyter Notebook for Python pulled up, and as you can see, I already have something typed into the code. This is just, it's a clone of a GitHub site that has this CHE tools in it, and that's going to let us get this the pressure of water that I talked about using the complex Antone equation. So I just already coded that in because we don't need to cover that in this video. So first thing I'm going to do is import the toolbox in here. Let's see, tools. And what this will let us do is just make it so I don't have to type in tools.che every time. Just make it CHE, make it a little faster. And then we're going to be needing the root solver so we can get our answers here. So I'm going to go and get that from SciPy. SciPy, SciPy, optimize, import root. All right. And then I'm just going to go ahead and define the R value because that's constant and that is not going to change. 8.314, and then make a comment so that we know the units because they're pretty important for the gas constant. All right, and so the first thing I'm going to do is we're dealing with water here, so we want the properties of water, and we're going to go ahead and use our toolbox, and one of the things in there is it lets us get the properties of the toolbox. So if I do this, and then I note that I'm trying to get water, and then so that will get it'll let me know that that's like whenever I use P, it'll be using getting the water information from the GitHub site. And so I'm going to go ahead and define our initial conditions. So we've got the volume total 0.01, and then we've got meters cubed. We've got the mass of water, and that is equal to 1, and that is in kilograms. And then we also have initial pressure, and that is equal to 101,325, and then that is in pascals. And then we need the initial temperature, and that's going to be 298, and that one is in kelvins. And then we also just need our final pressure that we know, and that is 2 to the 5th, and that is also in pascals. All right. So now we are ready to start solving. So the first thing I know we're going to need is the number of moles of air, and so I'm just going to go ahead and solve that now because that's not going to change for anything that we're doing. So I'm going to set that equal to, and then I'm going to try and talk less so that I don't make any mistakes when I'm copying over what we have in our notes, because there's a lot of parentheses involved. So we have our initial pressure minus pressure of water, and then we need that multiplied by the vapor pressure, or yeah, the volume of the vapor pressure, and the volume of the vapor pressure is equal to volume total minus the volume of water, and the volume of water is equal to the mass of the water divided by the density of the water, and we're going to use spelled it wrong, roll, and then we want that at the initial temperature, so I'm going to go ahead and do that. Alright, so now that we have the water, VVAP, so minus. Alright, so now we just need that divided by our gas constant times our initial temperature. And let me just go through and double check and make sure I didn't make any mistakes. We've got initial pressure. Oh, I need to define what our water pressure is using that Antone equation feature that I was talking about. And so we have that is equal to P. No, we got P dot PVAP. And then we want to give it our initial conditions there. All right. And then let's keep checking. VVAP is equal to the volume total minus the mass divided by the density, that's the volume, and divided all that by, make sure I had All right. Confident in that. It is ready to go. And so now let's just go ahead and define our function. I'm going to call it pressure equation. Alright, so we're going to need a variable. We'll just use y. And then make sure we have a colon so that it knows that it's a function. And I don't want it to be y the whole time, so I'm going to say our final temperature, which is what we're trying to solve for. And then it's going to give us an array when we type in, and we just want, there's only one value. Alright, so now let's start putting in what we need to solve for our root, with our root function here. So we see that we're going to need the pressure of air, and before we can get there we need the volume of the vapor pressure, because we haven't solved for that yet. So we're going to go ahead and solve for volume of the vapor pressure. And we did the same thing up here, just with the initial temperature, and we're using the final temperature here. So I'm just going to go ahead and snatch that from up here, copy it down here, and then just change it to the final temperature. Alright, and then we are also going to need the pressure of water, and that is equal to the Antone vapor pressure, so PVAP, at the final temperature. And then we're also going to need the pressure of air, and we see down here that that is equal to this there. So we are going to go ahead and do an air, set up some parentheses so we don't make any mistakes, multiplied by the gas constant, multiplied by temperature final, and then all of that divided by VVAP, or the volume of the vapor pressure. Perfect. So now we have all of the parts that we need, so we can go ahead and have the function return our values. And we want it to return the partial pressure of air plus the partial pressure of the water minus the final temperature. All right. And so now we're going to go ahead and solve. So the root function is going to require us to give it an initial guess. It's just how root solvers work. A good guess here, because we don't really know what the final temperature is going to be, but a temperature value we do know is the initial temperature. So we're just going to go ahead and guess the initial temperature and go from there. Oh, I made an error. Oh, that's a comma. I forgot I needed a comma, not the parentheses. Alright, and we see that the solution converged, which means it worked, and we see that our final temperature is at 366 kelvins. Alright, so we got the final temperature for our first set of conditions. So now we want to go ahead and code in for our secondary conditions here, where we don't know the total volume. So I'm going to go ahead and just start by defining a new function. And we're actually going to be using a lot of parts from this initial function we defined, so we're just going to reuse that code as much as we can. Obviously going to have to go to a new name here, and it's going to need to receive two guesses. We're going to want to give it a guess of what we think our total volume is, so we're going to give that the second input value. And then as we remember back here, with this new initial conditions where we don't know the total volume initially, we're going to need to change our volume of the vapor pressure to account for the difference in the volume of the water and the water pressure. So we're going to have to change the volume of our water equation. So we can go ahead and get rid of that here, and we're going to start new. So we're going to need the mass of the water minus the mass of the water vapor, and the mass of the water vapor is just equal to the number of moles desired, the number of moles of water vapor desired, and we're going to multiply that by, so I'm going to get another set of parentheses going, multiply that by the molecular weight of water. So then we just need to divide this quantity by 1,000 to get it into kilograms. Perfect. And then, so that gives us the mass of our water vapor pressure. Okay. So then we need to take this quantity, add another set of parentheses, and divide it by the density, so that we can get our masses in terms of volume. So again, we're going to use the rho at our final temperature, and there, that's what we need. So we are also going to need a new variable, because we have the desired number here, but we also need to know the actual number of moles of water vapor. So we're going to set that equal to what we have down here. So we've got the pressure of water times the volume of the vapor pressure, and then we've got that all divided by the gas constant times the final pressure. And then now we're going to be returning two things. We need to give it the we're going to give it our guesses for the final temperature and our guess for final volume, and then it's going to go ahead and give us the final temperature and final volume. So we need to make sure it can give us the final volume. So we're going to need it to return two values, and we just need the difference between the number of moles and the number of desired moles. So I just forgot a bracket. All right, and so now we need to give it a value for the number of moles of the water vapor desired, and so we're going to go ahead and set that equal to 0.3, and then make sure we remember it's in moles. And then we can just go ahead and solve. So we want the second equation, and then we need to give it two initial guesses. So I think we're going to go ahead and guess our initial temperature again, 298, just because it worked last time, and then our I'm pretty sure the volume of the container isn't really going to change, so a good guess, I think, is just going to be our initial volume, or our total volume from the first time we went and did this. So we see that the iteration didn't converge, it wasn't making good progress, so one of our initial conditions was guesses was wrong. I'm pretty confident about the volume staying the same, because the volume of the container isn't going to change. So that means our initial temperature guess, or our final temperature guess, was wrong. And we saw that the first time it was 366, so we'll just give it a better guess of closer to 360 and go ahead and run it again. And we see that the solution converged, which means we got our value. And the final temperature was 370, which was pretty far off from our 298 guess. So it makes sense that it didn't converge originally. And we also see that the volume was pretty much stayed exactly the same. So we have finished. Thanks for watching.